Hey guys, so today we're going to be looking at question 997 out of the Thermo textbook. We're going to start off by just reading the problem through. And we see that a gas turbine power plant operates on a modified Brayton cycle shown in the figure with an overall pressure ratio of 8. Air enters the compressor at 0 degrees Celsius and 100 kPa. The maximum cycle temperature is 1500 Kelvin. The compressor and turbines are isentropic, and the high pressure turbine develops just enough power to run the compressor. Assume the constant properties for air at 300 Kelvin with a constant volume specific heat of 0.718 kilojoules per kilogram Kelvin, a constant pressure specific heat of 1.005 kilojoules per kilogram Kelvin, an R value of 0.287 kilojoules per kilogram Kelvin, and a K ratio of 1.4. So today we're asked to sketch a TS diagram for the cycle and label the data states for A. For B, we're determine the temperature and pressure at state 4, the exit of the high pressure turbine. And for C, we're asked if the net power is 200 megawatts, determine the mass flow rate of air into the compressor in kilograms per second. So with this said, we're just going to look at the right for the assumptions that I already wrote out. And while it's not explicitly stated, we're going to have cold air standard assumptions. And while it does state that the constant properties are for 300 degrees Kelvin, we note that our inlet temperature is 273 Kelvin because that's what 0 degrees Celsius equals. Additionally, our inlet pressure is 100 kPa and our Tmax is 1500 Kelvin. And while we don't know where exactly that Tmax is, we will define that after we sketch our TS diagram. Additionally, I've written out that our pressure ratio of P2 to P1 is 8. Our power out is 200 megawatts, which is equal to 200,000 kilowatts. And we're also going to be neglecting kinetic energy and potential energy. Additionally, I rewrote our specific heats up in the corner just for the purpose of doing so. And we're just going to note that all those values are constant because of our cold air standard assumptions. Now to start out, we are going to draw our TS diagram. Get this a little straighter. Okay. Wrong axis. Okay, so initially we start out at 273 Kelvin at our state 1. And we know that the first stage of a Brayton cycle is an isentropic compression, and that's going to go up to our state 2. The next stage is going to be a constant pressure heat addition, and while we don't have pressure explicitly defined on any axis, we know that it's going to follow isobars in this curved fashion all the way up to state 3. And then we have to remember that we have 2 turbines for our isentropic heat, for our isentropic expansions. So we're going to make our first one about halfway down to state 4. And our second one's going to come down to state 5. Now remember our final process in the Brayton cycle is a constant pressure heat rejection, which is going to follow another isobar back to our state 1. We'll just draw in some arrows. Now before we move on, we're going to make note that we now see that at stage 3, we have our highest temperature of 1500 Kelvin. So we're just going to write this assumption down to our left, that T3 is equal to our Tmax is equal to our 1500 Kelvin. So now moving on, to start our part B, we're kind of just going to start at the beginning of the cycle, and we're going to just run through a few of the stages to determine some of the pressure and temperature values throughout the processes. So once again, we're going to note that stage 1 and 2 is our isentropic compression. And before we start, we're just going to make note up here that we know our P1 value is equal to 100 kPa. We know that our ratio of P2 to P1 is equal to 8. So quickly, just to figure out our P2 value, we're going to rearrange it. So that P2 equals 8 times P1, which is 100, to get P2 equals 800 kilopascals. So now, remembering that we're using air and our Cole standard assumptions, we're going to pull out our isentropic relations for ideal gases to solve this first part. And we're going to use the specific relation from temperatures to pressures a lot in this problem. We're going to note that T1 or T2 over T1 is equal to our P1 or P2 over P1 to our K minus 1 over K. Now, since we know our P1, our P2, our T1, and our K, we can easily solve for T2. And we're just going to rewrite it over here that our T2 is equal to T1 times we'll just write pressure ratio this time to our K minus 1 over K. And when we solve for that, we get that our T2 is equal to 273 times our pressure ratio of 8 times our 1.4 minus 1 over 1.4. And we get a T2 of 494.525 Kelvin. Now, before we move on to assessing our next state, we're going to come back to our problem statement, and we're going to highlight a very important assumption. So we see the high pressure turbine develops just enough power to run our compressor. So on our little diagram here, we're going to write that our work in for our compressor is equal to our work out of our high pressure turbine. Now, if we break this down into energy balance for these two states or two processes, we can relate a few of our values to get some other important values with this specific relation. So additionally, noting that we are at steady flow, we can say that our E dot in is equal to our E dot out for any stage during this process. So when we break this up, we note that our E dot 1 at the inlet of our compressor is equal to the E dot 2 at the outlet of our compressor. We're just going to write compressor because we're going to break this up into two energy balance equations. We also note that the E dot 3 at the inlet of our high pressure turbine is equal to our E dot 4 at the outlet of our high pressure turbine. We'll just put high pressure so we know that it's the first turbine. Breaking this down a little bit more, we know that for energy balance, when we neglect kinetic energy and potential energy, we can say that our energy at the inlet is equal to our mass flow times our specific enthalpy at state 1. And since there's work in at the compressor, we're going to add that. And that is equal to the other half of the equation, the mass flow times our specific enthalpy at state 2. And since there's nothing else, no work or heat on the other half of the equation, we don't have to consider anything else. Now, back to our turbine side, we're going to do the same thing, but since we have work out in this case, the only term on our left side is our m dot specific enthalpy at state 3, and that is equal to our w dot out plus our m dot specific enthalpy at state 4. Now, rearranging these equations in terms of power in and out, we get that our w dot in is equal to our m dot times our specific enthalpy at 2 minus specific enthalpy at 1. We get that our w dot out on the other side is equal to our m dot times our specific enthalpy at 3 minus specific enthalpy at 4. Now, before we move on, we're going to note that for ideal gases, the delta or the change in enthalpy is equal to our constant pressure specific heat times our change in T, since we know that for ideal gases, enthalpy is strictly a function of temperature. Now using this, we can simplify these equations once again to show that our W dot in is equal to our M dot times our specific heat constant pressure times our T2 minus T1. And the same thing on the other side is that our W dot out is equal to our M dot specific heat of constant pressure of T3 minus T4. Now, knowing that we want to set our W dot in of our compressor equal to our W dot out of our turbine, we can now equate these two energy balance equations. We get that our M dot Cp of T2 minus T1 is equal to our M dot Cp of our T3 minus T4. And noticing that our M dots are going to be the same throughout the entire process, as well as our constant pressure specific heats, we get that our T2 minus T1 is equal to our T3 minus T4. Now, we know our T1 and T2 from our initial conditions in the first problem that we solved up here. And we also know that our T3 is equal to our Tmax term from the TDS diagram that we drew at the beginning. So with that said, we can solve for T4 and note that T4 is equal to our T3 term of 1500 Kelvin plus our T1 term of 273 Kelvin minus the temperature that we solved for in the last part of 494.525 Kelvin. And this yields us a T4 of 1,278.475 Kelvin for our T4. And that is the first half of our B problem. And once again, knowing that we have an ideal gas and we can use our ideal gas isentropic relations, we're going to evaluate our stage 3 to 4 now, which we know, once again, is isentropic, but this time is our first expansion to the high pressure turbine. Now, our T4 over our T3 is going to equal our P4 over our P3 to our K minus 1 over K. Now, while conventionally we know our pressure values and we are solving for temperature, this process is going to kind of be a little bit weird because now we're solving for our P4. Additionally, you might note that we have not yet defined a P3 term, but if we come back up to the top, we can note that at P3, or to get to stage 3, we undergo a constant pressure heat addition. So therefore, our P2 value will equal our P3 value, which will equal 800 kPa. Additionally, before we move on, we're going to do the same thing for our 5-to-1 process, knowing that it is constant pressure. So our P1 is going to equal our P5, which is going to equal 100 kPa. So with this said, we're going to rearrange this equation down here again, or just we're going to rearrange it, but this time it's going to look a little different from what we've done before. So our P4 value is going to equal P3, and this is going to be K minus 1 over K, and that is going to be our root of our T4 over T3 ratio. Remember, this is a root, not a power. So with this said, we're going to simplify it, that our P3 of 800 kPa that we just determined, and this is our root 1.4 minus 1 over 1.4 to our T4 that we just solved for of 1,278.475 Kelvin over our Tmax of 1500 Kelvin. And when we do this math out, kind of wonky, but when we do it out, we get that our P4 is equal to 457.29 kilopascals. And that is our second part of part B. So now we're just going to divide this up. We're going to come back to the top over here, and we're going to kind of just continue through our stage process from our 4 to 5. And we're going to note that this is our, once again, an isentropic process, but this time it's our second expansion through our low pressure turbine. So with this said, we have once again our temperature to pressure isentropic relation, which equals T5 over T4 is equal to our P5 over P4 times our K minus 1 over K. And with this said, we're going to simplify this to T5 is equal to T4 times the P5 over P4 to our K minus 1 over K. Now noting that we already defined our P5 up here, which is equal to our P1, and we just solved for our P4 and T4, we have enough information to get our T5. So writing this out a little bit, we get our 1,278.475 times our pressure ratio, not the given pressure ratio, but this new ratio of 800 kilopascals over our 457.29 kilopascals to our 1.4 minus 1 over 1.4 power. And this yields us a T5 value of 828.067 Kelvin. Now that while that was not specifically asked for, it will help us in our last part, which we have to use energy balance to find our mass flow. Now, while it does ask for our mass flow throughout the through the compressor, we're going to note that since this is steady flow, our mass flow is going to be constant throughout the entire process. So since we know that our power out is coming out of the low pressure turbine, stage 5 of 200 megawatts, we're going to evaluate it at that state. We're going to have our energy balance at that state. And with that said, remember that our delta E is equal to 0 for steady flow. So our E4 value will be equal to our E5 value. And when we break this up again, we get that our mass flow times the enthalpy at state 4 is equal to our mass flow of enthalpy at state 5 plus our power out. Now also remembering the ideal gas assumptions with enthalpy being that it's strictly a function of temperature, we can once again break these down to be m dot Cp, m dot Cp of T4 equals m dot Cp of T5 plus our W dot out. And when we put this in terms of our W dot out, we get that our m dot Cp of T4 minus T5 equals our power out. So finally, knowing that we want to solve for our m dot out, sorry about that. If we want to solve for our m dot out, we're just going to rewrite this equation once again in terms of our m dot out. So you get that our m dot out equals power out divided by our Cp value times the difference between T4 and T5. Now noting that we're given our power in megawatts and we defined it in kilowatts up in our assumptions as 200,000 kilowatts, we get our 200,000 power in kilowatts over our Cp of 1.005 kilojoules per kilogram Kelvin times our T4 of 1278.475 minus our T5 that we calculated up here of 828.067 Kelvin. And when we do that division out, we get that our m dot is equal to 441.83 kilograms per second. And that is our final answer. Now, before we leave today, we're going to come back up to the question, and we're going to note that the given answers for A, the question gives us, are 1,279 Kelvin, which is what we have for our T4 value down here. And our P4 value is 457 kPa, which is pretty close to our P value there. Additionally, the C value that's given is 442 kilograms per second, and that is exactly what we got for our m dot value down here. So with that said, I hope you learned something today, and we'll catch you later.